This video is going to show another example of a linear system. In this case, the origin is going to end up being a source instead of a sink. If you watched the two videos that I've done so far about saddle points and sinks, you'll recall the examples that we did there gave us the origin as a saddle in the first video and a sink in the second. This one is going to end up being a source. Before I delve into this example, first thing I want to say is that you can't always tell. It's pretty hard to tell just by looking at the matrix itself whether it's going to give you a saddle, sink, or source. Or there are other kinds that we'll see in the future, a spiral sink or a spiral source, or what's called a center, where you get infinitely many periodic solutions when you get a center for a linear system. It's hard to tell just by looking at the matrix, so you really do need to go through these computations. Just because most of these numbers are positive is no guarantee that I'm going to have a source. I do need to go through most of the computations. Let's go ahead and quickly check that the origin is the only equilibrium point. The determinant of this matrix is going to be 4 minus negative 2, which will be positive 6, non-zero, so the origin is the only equilibrium. The eigenvalues. For a two-dimensional system like this, you can use this equation for the eigenvalues. The trace is 5. The determinant, as we've already seen, is positive 6. And I've made the numbers work out nicely again to get 5 plus or minus 1 over 2. 5 minus 1 over 2 is going to be 2. 5 plus 1 over 2 is going to be 3. So your eigenvalues are 2 and 3. What about the eigenvectors? For the first eigenvalue, 2, I think about taking this matrix minus lambda times the identity and plugging in 2 for lambda, in effect subtracting 2 from the upper left corner and 2 from the lower right corner to give me the following system of equations. 2x minus 2y equals 0 and x minus y equals 0. You should take a few seconds to confirm that in your head, compare these two things. Think about what happens to the coefficients when you do the subtractions in the diagonal, and don't do any subtractions on the off diagonal. And these are redundant. You get y equals x. And so one example of an eigenvector for this eigenvalue is the vector 1, 1. For the other eigenvalue, 3, I subtract 3 from the 4 and from the 1 to get the following system of equations. X minus 2y equals 0 and x minus 2y equals 0 again. Once again, you should take a few seconds to compare those two. Matrix up here and the system down there to confirm that's what you would get. This time I'll actually solve it for x in terms of y. X equals 2y. And so I'll fix y to be 1, and then the equation determines that x is 2. If I picked x to be 1, then y would have to be a half, and I like to avoid fractions when I can. So we can pretty quickly, with enough practice, this can be done in just a couple minutes, we can pretty quickly write down the general solution like this. Arbitrary linear combination of these two particular solutions. And I won't bother solving an initial value problem on this particular video. But we should think about the phase plane. We need practice with that. The origin is your only equilibrium. If there were other equilibria, and with nonlinear systems there definitely could be, you'd want to plot those too. Even with linear systems, when you get a determinant equal to 0, you're going to have more than one equilibrium. You're either going to have a line of equilibria, which is the usual case when the determinant is 0, or in the very special case of the matrix being the zero matrix, where every entry of A is 0, the entire plane would consist of equilibrium points. But that's just one example. That's a very, very special case. It only happens in that one example. Because the eigenvalues are positive, solution curves are going to go away from the origin as t increases. They also will go back toward the origin as t decreases, but we will draw the arrows on these parametric curves pointing away from the origin as t increases. Once again, we draw the eigenlines, sometimes called eigenspaces. This one corresponding to the eigenvalue vector, let's see, it was 1, 1. And the other one is not too far away. It's going to be along the line with slope 2. It's corresponding to the second eigenvector, the eigenvector 2, 1. Lambda 1, for a reminder, was 2, and lambda 2 was 3. Unfortunately, this is one of those mistakes that I never ended up fixing. I made a mistake when I drew that line of eigenvectors, the eigenspace for that second eigenvector, 2, 1. I drew it so that it had a slope of 2, but if you think about it, it should have a slope of 1/2. Okay, and I never fixed that mistake, so you should make sure in your notes that you draw a slope of 1/2 instead of that slope of 2. And it's going to result in your phase portrait looking a little bit different than the phase portrait that I eventually end up drawing, so you'll need to figure out how to make that adjustment. Solution curves are going straight away from the origin along those lines. What happens as t goes to infinity? Do most solution curves approach one of these lines in particular, or do they sort of go off wherever they feel like it? As t approaches infinity, both of these terms grow. Imagine k1 and k2 are both non-zero. But that one grows a lot faster because of the 3t as opposed to a 2t. Relatively speaking, this one grows a lot faster. What's the practical consequence of that? The practical consequence is that as t grows big, most solutions, if you're looking at a scale that's very far away, very big scale, like negative a trillion to a trillion for x and the same for y, most solution curves will seem like they're approaching this, or maybe a better way to say that is they'll seem like they're parallel to that vector. They'll still be far away from it if k1 is non-zero, but they will seem to be straight with a slope of 2. Back in this picture, that means that as t goes to infinity, your solution curves tend off toward this line. They sort of curve off this way. Let's also think about what happens as t goes to minus infinity, so we can look at the behavior near the origin. As t goes to minus infinity, both of these decay to 0. Which one decays faster? As t goes to minus infinity, this one decays faster. You've got e to a bigger negative power than that one. This one goes to 0 faster, so solution curves, in a sense, get closer to the line through that eigenvector, the other one, the one whose eigenvalue is closer to 0. That's the one they are tangent to as t goes to minus infinity. So this one is going to be tangent to that vector, that eigenline. This one also, as I imagine time going backwards, will come in tangent to that, but I want to draw the arrows going the other way because it's really a source. In making these drawings here, I'm just imagining t going to minus infinity now. to bring me back toward the origin. And there are plenty of other solutions. We just want to get the general feel after this point. You can just draw in some others. There we go. That's the source that we have at the origin. Maybe in this video it would be worthwhile to take the time to do an analysis like the book does in thinking about what the slope of these solution curves becomes. In this case, I'll let t go to minus infinity. What is dy dx along the solution curve? Well, you can look up in a calculus book that the slope along a parametric curve is the ratio of the rates of change of the individual components. The derivative of y with respect to t divided by the derivative of x with respect to t. So what I can do is I can take my general solution right here, write down x, little x and little y, the components, and differentiate those and see what I get. Let's again imagine k1 and k2 are fixed but non-zero constants. For x equals k1 e to the 2t plus 2k2 e to the 3t, because of the 2 right there. The derivative of that I'm going to need the chain rule for because of the 2 there and the 3 there. If you do that, here's what you'll get. You'll get 2k1 e to the 2t plus 6, 2 times 3, k2 e to the 3t. For x, oh, excuse me, that was x, mistake. 2k1 e to the 2t plus 6k2 e to the 3t. For y, go to the second component, k1 e to the 2t times 1 plus k2 e to the 3t times 1. Differentiate that, you get 2k1 e to the 2t plus 3k2 e to the 3t. And we can ask then, what is the limit of this slope as t goes to negative infinity? This is the slope along the solution curve. So there's a t in the background. This slope, if we're realizing there's a t in the background, does depend on t. And now we can ask, what is the limit of that as t approaches minus infinity? And let's take a guess as to what it will be. Going back up to here, as t goes to minus infinity, these solution curves, except for the one along the second eigenvector, are approaching the origin along this other eigenvector, the eigenvector 1, 1. The slope should be 1 as t goes to minus infinity. What happens as t goes to minus infinity here? In this particular fraction, both the top and the bottom are approaching 0. It's a 0 over 0 situation, a 0 over 0 indeterminate form. Here's where it's tempting to use L'Hopital's rule, but L'Hopital's rule will not be helpful. Instead, you'll see if you try it that it just doesn't help. It makes things worse, in fact. It's not that it's not true, it just is not helpful. Instead, what's helpful is to multiply the top and the bottom of this fraction. Well, should it be by e to the negative 2t or e to the negative 3t? You can experiment with both. Let me see if I can do it in my head here. If I multiply the top and the bottom of this by, say, e to the negative 3t, those e to the 3t's will become 1's, and these e to the 2t's will become e to the negative t's, which will be helpful in thinking about, let's see, limit as t goes to negative infinity. I guess that's not helpful. It's trying to, because if those are e to the negative t's, as t goes to minus infinity, those will go to infinity. So it looks like I need to multiply by e to the negative 2t instead. Multiply the top and the bottom by e to the negative 2t. Those e to the 2t's go away, and the e to the 3t's become e to the t's. And that's okay. This is going to be helpful because e to the t goes to 0 as t goes to minus infinity, but these don't. You get 2k1, at least if k1 is non-zero, plus 0 over 2k1 plus 0 in the limit, which is going to simplify to 1 as t goes to minus infinity. The only case where this calculation wouldn't work is if k1 is 0. But if k1 is 0, that's going to correspond to a solution along that second eigenvector. And that has slope 2. So for solutions along that, you get a slope of 2. My final comment, before I tell you a little joke, is that if we are trying to generate examples of sources, and we also happen to have an example of a sink. This was the example from the video with the sink example. The sink example video. If we have an example that we know is a sink like this one was, there is a way to use that example to generate an example that's a source. Think for a second. What do you think you would do? Think in terms of the vector field. For a sink, all the vectors in the vector field are pointing toward the origin. If you just switch the direction of all those vectors, you would get a source. How could you switch the directions of all the vectors, except for the 0 vector, in the vector field? Just put a negative sign in front of the original matrix. That's going to make all the outputs of the vector field go in the opposite direction. So the following matrix the following system, positive 4, negative 1, negative 2, positive 3 as our matrix. Compare that with this one over here, is going to give us a source. So if you're trying to generate examples, and you should check that on your own, you should find the eigenvalues and eigenvectors. And in fact, if you made the phase plane, they would be the same curves, but the arrows would pointing in the opposite directions. If you're trying to generate an example of a sink or a source when you already have an example that's a sink, you can just negate all the coefficients. And vice versa. If you have an example that's a source, you can obtain a sink by negating all those coefficients. If you have an example that's a saddle point and you negate them all, I guess you'll still get a saddle point. It doesn't change the type of equilibrium. This switching back and forth between sinks and saddles reminds me of something mathematicians do a lot. They use previous results to prove new things. It reminds me of a joke. A physicist and a mathematician were given a problem. They were told, imagine there's a burning house, a fire hydrant, and a fire hose not connected to the fire hydrant. What should you do? The physicist said, connect the hose to the fire hydrant, then use that fire hydrant to put out the fire. The mathematician came along, and they're like in separate rooms or something, so they can't hear each other, but the mathematician comes along and says, connect the hose to the fire hydrant, then put out the fire. They both got it right. Then they were asked another question. Suppose there's a house and a fire hydrant and a hose connected to the fire hydrant. What should you do? The physicist says, I just walk on by because there's no problem to solve. The mathematician says, well, I disconnect the hose from the fire hydrant, then start the house on fire, and then I've reduced the problem to another problem that has already been solved.